Hello, welcome to Maths with EJD. In this video, we'll be talking about the measures of shape. The measures of shape. Been dealing with a lot of with some measures all along. The first was measures of central tendency or location. Okay, talking about the measures now. We had location or central tendency. Okay. Afterwards, we talked about measures of position. Then after that, we talked about measures of dispersion or variability or variability, variability. And then, of course, so now we're talking about measures of shape. Measures of shape. Measures of location, of course, were mean, median, mode. Okay. For measures of position, we talked about percentiles. So for measures of location, they are single values that represent the whole data. We're talking about mean, median, and mode. Then for measures of position, they actually tell you where a particular data point is located in the whole data set. So then we talk about percentiles, deciles, and quartiles. And then that took us to measures of dispersion and variability, where we talked about range, variance, standard deviation, and interquartile range, IQR, interquartile range. Okay. And from there, we saw how interquartile range can help us identify outliers in the data set. Then now we're talking about measures of shape, which basically talks about skewness, how skewed a data is, skewness and kurtosis. Okay. So that's going to be our focus for now on this video. And this video, measures of shape. So let's go. First of all, when we talk about skewness, what is that? You should know that skewness measures, of course, since we talked about measures of shape, right? Tells you the shape, it simply tells you the shape of your data set, how your data is distributed, right? So skewness, so in talking about the shape now, we have skewness and kurtosis, and skewness measures the asymmetry of a data distribution. Okay. Measure the asymmetry of a data distribution and the relationship between the mean and median. The relationship between the mean and the median helps to determine the direction of the skew, the direction of the skew. Okay. For instance, in a perfectly symmetrical distribution, in a perfectly symmetrical distribution, so you'll see that the mean equals the median. So when the mean is equal to the median, then you have a perfectly symmetrical distribution. So in that case, you say that skewness is equal to 0. So when mean is equal to median, the skewness is equal to 0. Okay. Now, when this distribution is asymmetrical, there are scenarios when the distribution is asymmetrical, and the distribution is asymmetrical. Okay, I was trying to manage the space. It's asymmetrical. So what happens? We have two scenarios we can have a positive skew, can have a positive skew. In that case, we say that the data distribution is right skewed, skewed to the right. It's right skewed. And what happens in this situation is that the mean, the mean is greater, the mean is greater than the median. The mean is greater than the median because extreme extreme large values pull the mean to the right, pull the mean to the right. Okay. To drive the point home, see what happens when something is positive or right skewed. So, I mean, just a rough kind of thing here. So you have for something that is right skewed. Oh, I should have drawn something up here, but okay, I can still do that now. So okay. What can I do now? What can I do? What can I do? For perfect symmetricity, okay, I can still try. So imagine having this, and then you have the distribution. It's just perfect like this. So here you see the mode, the mean, and the median. They are all in one place. Okay. In that case, you have, I mean, my representation is not even looking perfect, but I mean, the idea is that you have perfect symmetricity because the mean, median, and mode all align in in the center like this. Okay. So, but when you talk about positive skew, for positive skew, we've already said that the the mean is greater than the median. The mean is greater than the median. Now, see what happens in that case. You have it, you have it shooting up here, and then it spreads out, and then it spreads out on the okay, let me try. And then it's spreads out somewhat this way. So here now, you can have the mode here. The mode is here. And then you have the median. You have the median somewhere here. So you have the median around here. And then you now have the mean somewhere here. So in that case, so you see there you have a long right tail. You have a long right tail. This is the tail now. Long right tail. So there you say it is positively skewed up or right skewed. So because the mean is greater than the median, because probably you have some outlier data that is making it spread out that way. Okay, so that's the first situation for positive skew. Now let's talk about negative skew. What happens with negative skew? Negative skew, or what you can call that the data distribution is left skewed. Left skewed. Now, so for left skewed now, the mean is less than the median. The mean is less than the median because extreme small values, extreme small. So here it's extreme large values, right? So you have large values that are outliers. Here you have large values that are small values that are outliers. So because extreme small values pull the median, pull the mean to the left, to the left. Okay. So in that case, the graph will look, of course, left skewed. So you have this now. But in this case, you're going to have a long left tail. You have a long left tail. So it's something like this. So you have a long tail this way, and then everything comes down this way. You try to make it good a bit more. I'm not very good with all this drawing sometimes. Okay, something like this. So here now, of course, you have the peak here is the mode. You have the mode here, and then now we say that the mean is less than the median. So the median is somewhere here. In the other case, the mean was in the center. I mean, the median, oh yeah, the median is it's still in the center, but the mean is now smaller than it. So you have the mean, say you have the mean somewhere around here. Okay. In that case, you say it is left skewed. And the big deal is that it has a left, long, long left tail, which is this now. So you say it's negative skewed. Okay. So that's the thing about skewness. Interestingly, there's a formula for skewness. Let's see that. So um the formula for skewness, which you can call SK, is this, that SK equals, actually this is uh sample skewness now, sample skewness. Okay, we'll just focus on that. I'll just write the formula. I won't really apply it. So the formula for sample skewness, SK, is n over n minus 1 into n minus 2, summation from I equals 1 to n of x bar, xi minus x bar, all over s raised to power 3. So this is the formula for sample skewness. Okay, the formula for sample skewness. But what do the terms mean? Where n is equal to number of data points. Number of data points. Okay. Then you have xi, which is each individual data point, each individual data point. Okay. And then you have x bar, which is mean of the data set, mean of the data set. You already know how to find this, right? And then you have small s to be the standard error, or you can call it the standard deviation for the sample, standard deviation of the data sets, of the data set. Okay. So this is the formula for sample skewness. All right, so let's look at some examples. Look at some examples. So first one, um, consider the ages. We'll call it example one. Consider the ages 20, 22, 21, 23, 24, 25, 26, 30, and 40. Okay, if you consider that, right? So the mean, so you can compute the mean. The mean is 25.22. If you calculate that, the mean is 25.22, and it is greater, the mean is greater than the median. The median is 24. Okay. I'm just being lazy. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is, let's rank and be sure the median is actually 24. So this is the smallest is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, great. So the middle number is actually 24. So we are good. All right. So because to get the median, right, you have to rank. So if you rank, actually 24 is the median. Perfect. So the mean is 25.22 and it is greater than the median, which is 24. So what does that mean? It's indicating a right skewed, because mean is greater than median. So we have a right skewed distribution, right skewed distribution. So if you have ungrouped data like this, one of the easiest ways to know how skewed the data is to find the mean and the median. So once mean is greater than median, then it is right skewed. If median is greater than mean, then you have a left skewed distribution. Okay. So let's take example two. Example two, that can go with grouped data. Okay, of course, maybe I shouldn't worry naming whether it is grouped or not grouped. So here we have a score range. We have a score range, and we have frequency for that. Score range and frequency. So for 0 to 10, you have one person with that score. 11 to 20, you have three. Then you have 21 to 30, that's five. Then you have 31 to 40, that is four. And lastly, 41 to 50, you have one person there too. So this is grouped data now. So with this, it's easy to draw a histogram, right? You can draw a histogram. Let's give it a try. So imagine you have this, and then for the first one, 0 to 10, let's say this is 10, this is 20, 30, 40, and 50. Okay. So if we need to do this now, 0 to 10 is only one. Okay, we also have to do the numbering here. So biggest is 5. So let's do that. This is 1, 2, 3, 4, and 5. Okay. So 0 to 10, 0 to 10 is actually the frequency is 1. So we're talking about score range, right? So here, this is score range. And this side is the frequency. So you have 0 to 10. This is 0 to 10. And then 10 to 20, 11 to 20 is 3. So this goes up like this. Yeah. Okay. So 10 to 11 to 20 is 3. Okay. Then you have 20 to 30, 21 to 30 is 5. So we go up like this. 21 to 30 is 5. Okay. Then 31 to 40 is 4. So something like this. 31 to 40 is 4. Because we have all these lines demarcating. Then we have 41 to 50 to be 1 again. Yeah, something like this, right? So you can see there's a bit of symmetricity, but then the mean of the distribution is less than the median. Still, of course, we can do the more practical thing, compute the mean. Okay, find the mean, find the median. Whatever that is, you can decide. And we've done this a couple of times, so I'm not talking about that again. So here, in the other case, right, the mean was greater. Here, well, from even the distribution itself, right, if we look at it, looks like it's skewed to the ah should I go through the pain? I don't want to. Yeah. Okay. Well, you can calculate the mean, calculate the median. You can just take that as a kind of assignment. I've done this a couple of times. So then you can decide based on the mean and the median what it is. If since the picture is not giving, it's not looking as clear enough to decide. Okay. It's not looking clear enough to decide. Well, the mean less than the median, not too sure of that. Okay, So you can compute the mean and the median and decide what happens there. All right. So let's move on to kurtosis. So let's move on to kurtosis. So we've already seen that skewness talks about the asymmetricity, the asymmetry of the data distribution. What does kurtosis talk about, right? Let's see. Kurtosis measures the tailedness, or should we say tailedness? So you're talking about the tail now. It measures the tailedness or the presence of outliers, the presence of outliers in a data distribution. So skewness talks about symmetry, while this one talks about tailedness or the presence or absence of outliers in a data distribution. So, okay, while skewness focuses on asymmetry, right? While it focuses on asymmetry, kurtosis evaluates the height or the peak, and the heaviness, heaviness of the tails. Okay. Now, kurtosis is classified, into three types, based on the relationship, based on the relationship of the peak and tails compared to a normal distribution. So in this case, we have what you can say a data distribution is mesokurtic. So that means normal distribution, normal distribution with medium tails, normal distribution with medium tails and a peak, medium tails and a peak. In that case, the excess kurtosis is 0. Okay. So that's just more like when everything is fine. So the analogy in skewness would be that case where you had perfect symmetry, you know. So then we have the second type of kurtosis, which is leptokurtic. So leptokurtic distribution will be distributions with a sharp peak, and heavy tails, sharp peak and heavy tails. So in this case, you have positive excess kurtosis. That means you have kurtosis greater than 0. So this indicates a higher likelihood, a higher likelihood, of outliers, Okay. Then lastly, you have what you can call like a platykurtic data distribution. So this will be distributions with a flat peak, like platykurtic is like a plate. with a flat beak and light tails. Light tails. So in that case, you have negative excess kurtosis, negative excess kurtosis, which is less than 0. This indicates fewer outliers, Okay, so let's talk about. Let me draw a diagram just to drive the point home. So in this case now, you have this, so that when so imagine you have something like this. Okay, then next you have something like this. That's not so good. Let me try again. You have something like that. And lastly, you now have something like this. So though not looking perfect, but we can use this. So this is what you call leptokurtic, because it has the peak is sharp, although it's not looking that sharp. So you have it projecting upward like that. So it's as it goes higher, it gets slimmer. I didn't do a good job drawing that. So in that case, we say the kurtosis. So it's leptokurtic, right? Meaning the kurtosis is greater than 3, okay? And then for the next one, we have this to be, this is the normal thing. This is mesokurtic, and here the kurtosis is equal to 3, okay? And lastly, we have the plate, that's platykurtic. That means the kurtosis is less than 3, okay? So that's what that looks like. So, like I said, right, as it's going up, it's getting slimmer. So I didn't do a good job, but I'm going to show you later on a proper graph as much as possible. Okay, so I think that's what that will be, but I can just make mention of, yeah, very important, the formula, right? We need to talk about the formula. Very important. So the formula for kurtosis, by the way, sample kurtosis, because there's also one for the population, will simply be k equals n into n plus 1 divided by n minus 1 into n minus 2 into n minus 3, summation from I equals 1 to n of xi minus x bar all over s raised to power 4 minus, this one is plenty, minus 3 into n minus 1 squared all over n minus 2 into n minus 3. So this is the formula for kurtosis. So if you ever have a need to compute the kurtosis for a particular data set, you can use this. Okay. So of course, what do the values mean? So we have n, of course, is the number of data points. Then you have xi. Xi is each individual point. Then you have x bar, which is mean of the data set. And lastly, you have S, which is standard deviation of the data set. Standard deviation of the data set. So that's the formula for kurtosis. So, I mean, some examples, for instance, if you can have mesokurtic data set, which is height of adults in a random sample, often follow a normal distribution, which results in a mesokurtic data set. Okay. And then we can have some specific examples like that. So don't forget, positive skew mean is greater than median. Negative skew mean is less than median. And when mean is equal to median, you have is a perfectly symmetric data distribution. Now, I also would like to show some of these graphs in Python. Okay. So yeah. So here let's see measures of shape, right? That's skewness and kurtosis. So of course I won't explain the code because that's not the purpose here. So the first side is to define a function that helps us plot. So talking about skewness, now we have symmetrical or normal distribution. So if I run this now, you see it's symmetrical. So it just goes, it's properly distributed, just like what a normal distribution should look like, right? So in this case now you have the skewness is almost zero, you know. So it's like that. Then we can also have a positive or right skew, like we said before. So you can see most of the data is on the right hand side, is on the left hand side, except that. So we said it is positive skew. So you have it spreading to the right because probably you have few high values that drags it down, that makes the mean bigger than the median. Okay, so this is positive skew. And then we can go for negative skew now. Negative skew, you have this. So most of the data is on the higher side, right? But then you have some small values that makes the tail very long towards the left. So that's a negative skew, or what you can call a left skew. And then we go to kurtosis, we talked about the tailoredness, or what you can call the what's that thing now? Tailoredness, or oh, I've forgotten what that word is. Okay, so here now we have a mesokurtic distribution, which is like the normal situation. So it's almost like a perfectly distributed symbol. Not quite, but then this is as close as it gets to it. So here we have a mesokurtic distribution, which is normal. And then we can have leptokurtic, which is sharper. So you can see it's sharper instead of this one that is spreading out. So here it's sharper. So we have a sharp peak and heavy tails. Okay, so that's leptokurtic. And then when you talk about the platykurtic kurtosis, you have, so you can see you have flat peak and light tails. Okay, the tails are not so, you don't see the tail protruding a lot. So that's what the point has been. Thank you so much for being here up till this point. If you have not subscribed to this channel, be sure to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. Don't forget to comment, like, and share. See you next time. Bye.